Hello, here's another circular motion question, which hopefully we'll see is quite similar to the previous ones, even if it might on the face of it look quite different. Okay, so they've given us a diagram, so we do the usual thing of seeing what's in the text that isn't on the diagram. Particle of mass m, okay, they haven't actually marked the particle on, so that's something new. Suspended from a fixed point O, light inextensible string of length L, that's all on the picture. Particle hangs in equilibrium at the point R, vertically below O. Right, so that's where we're starting. Particle is set into motion with horizontal velocity U, so they haven't put that on. So we start with U, so that it moves in a complete vertical circle with center O. Point T is on the circle, such as that angle. Right, so the only things I didn't put on there are M and U. Now we've got to find lots of different things here. We've got to find the speed of the particle at T, tension of the string at T, tension of the string at R, and then the minimum value of U for it to keep going in circles. Right, so we're talking here in terms of speed. So you can see this in the first part of the question. We're getting the speed at point T. So it's kind of pushing us into our v squared over r centripetal acceleration, where of course r is L in this case. That's why I've put that formula in quotes. So let's crack on with the first bit then, see how we get on. So the speed of the particle at T. So we're going to want conservation of energy here for this first bit. So conservation of energy. So energy at the start, which is going to be a half mu squared, is going to be the energy at T. So that's a half m, let's call it v squared, plus mg, well, h, and h is going to be L minus L cos 30. L minus L cos 30 degrees. So we've just got to tidy that up, and then we've got what we need. So all of the m's cancel. We can multiply through by these 2's, but we'll do that maybe in a moment. Let's clear up this issue here. If we got 1 minus root 3 over 2, that is 2 minus root 3 multiplied by a half. So we've got halves we can get rid of all the way through here. So u squared is v squared plus g times L 2 minus root 3. And what are we trying to get? We're trying to get the speed. So we want v. Actually, let's just go straight for v rather than rearranging it to v squared, because it's not much of a rearrange, is it? U squared minus gl 2 minus root 3, and the square root of all of that. So that's our v. So that was actually nothing to do with circular motion, really. It's just one of our conservation of energy questions, relatively straightforward. Now we have to find the tension of the string when the particle is at point T. So this is where we're going to be stepping into circular motion. So we're going to want to do our F equals ma on this. So let's add our forces in. We've got mg going downwards, and we've got the tension in the string going towards the center of the circle. So if we're going to do Newton's second law on this, resolving towards the center of the circle, we're going to have that T minus mg cos 30 degrees is going to be equal to mv squared over L. Just changing the R to L. So yeah, I mean, we're pretty much here. We know what v squared is, because we have to show this. You see here, they want it in g, l, m, and u. They want it as a function of those, not of v. So we're going to have to get rid of this v squared, but that's fine. That's what we worked out in the previous part. And we got our mg cos 30 sitting around. So let's stick all of this in. We've got T is going to be equal to mg root 3 over 2 plus mv squared over L. So that's going to be mu squared over L. I'm splitting this into two terms because we're going to have some mg's kicking around. Minus mg 2 minus root 3. Yeah, multiply those L's cancel in the other term. So all in all, we've got T is going to be mu squared over L. We've got an mg root 3 over 2 plus another mg root 3. So that's going to be mg, what did I say there? We've got half of it plus a whole one. So we've got 3 over 2 mg root 3 minus minus 2 mg. Okay. So I suppose, yeah, we could factorize that last bit. So what we got, mu squared over L plus mg 3 root 3 over 2 minus 2. So that is our value of T. Yeah, a little bit messy, but it's just keeping track of the algebra really rather than anything else. I don't think we can simplify it down any more than that. So that was fine. Find in terms of G, L, M and U, again, the tension in the string when the particle returns to the point R. Okay, well, I mean, whether it's returned to point R or started at point R or whatever, I mean, we're still doing exactly the same thing here. We're doing this is the same question. We're doing F equals MA again, but we've now removed the cos 30 part in this. So we've got mv squared over L is T plus mg. And that's, yeah, pretty straightforward. I mean, minus mg is what I meant, not plus mg, because it's in the opposite direction. So yeah, just drawing in, if we were doing it here, we've got mg going downwards, we've got T, our new T going the other way. So yeah, we're just doing that. We've got T minus mg is equal to mv squared over L. So we're just doing the same thing that we had before. And in this case, V is U. So it's even easier. We can just change that V to U because we're back where we started. So yeah, we've got that T is equal to mu squared over L plus mg. So yeah, that's a pretty straightforward part of the question. Right, now we're getting on to this last bit here. They're saying the particle makes complete revolutions. Find in terms of G and L the minimum value of U. Right, so this is similar to if you've seen any of the questions that they're kicking around, even one of the ones I've done in a previous video on the washing machine. It's the same thing. I mean, I know we've got here the tension is pulling the object towards the center, whereas in the washing machine we've got the drum of the washing machine that's pushing the object towards the center. But the effect is much the same thing. And if we're going to stay in circular motion, then in this case we need to have continual tension in the string. In the case of the washing machine, we need to have continual reaction force from the drum. This is showing, having tension in the string means the string hasn't gotten slack, so it's still staying in a circle. As soon as the tension disappears, the string's gone slack, so we're not staying at the radius of L, so we're not in a circle anymore because the radius has changed. That's what's happening as soon as the tension disappears. It's the same in the washing machine with the drum. As soon as the reaction force has disappeared, then the clothing isn't in contact with the drum, so it can't be at the radius of the drum, so it's no longer in the circle. So although they might on the face of it look quite different, oh yeah, we've got a string pulling or we've got a drum pushing, it's the same thing. We've still got a force which we need to make sure doesn't drop down to zero, because as soon as that's gone, yeah, that's our limiting point really. When it's dropped to zero, we're at the point of losing the full length of the string, and we're at the point of coming away from the drum. So we can't approach this last part of the question of just saying, oh well, providing it's still got velocity at the top. Some people approach this, say, well, minimum value of U is the velocity required to get the particle up to the top here. But if you get up to the top and all of the kinetic energy has been converted into potential energy, and we got no velocity left, well, we're just not, well, A, you couldn't physically do that because then it would drop straight down, where you can't move up to the top, move round in a semicircle and then just suddenly, oh, we've got no velocity, we'll drop down. You have to have some velocity. But if you don't have enough, it's going to start just sort of falling away. It's going to go into a free fall projectile situation rather than having the tension in the string. So we can't just do a conservation of energy approach. We need to look at it as what is required in order to keep tension in the string at the top. So well, I'm going to need to go onto a new sheet for this. We don't really need the picture there anymore. So yeah, how are we going to go about doing this then? We need to have, when we're at the top of the circle, then we've got mg plus t is going downwards, and that has got to be equal to mv squared over L, they were calling it, weren't they? We need to have t being greater than 0, or well, greater than equal to 0. When it hits 0, that's the point that the string starts to, we're going to be moving towards having a slack string. But we also know from this that we do have the conservation of energy for the v squared. So we can say that our half mu squared, our initial energy, has gone to the half mv squared, which is our kinetic energy at the top, plus the change in the potential energy, which is mg times h, and h is 2L, 2 lots of the radius, because that's the height that we've raised things through. So this is going to give us our v squared, because we can cancel all the m's, multiply everything by 2, so we don't have any fractions kicking around. We've now got the v squared is u squared minus 4gl. So that's how our velocity has dropped off. Now we can whap that into here, because we, first of all, rearranging this, we're saying that t is mv squared over L minus mg, and that needs to be greater than or equal to 0. That's how because the tension needs to be, it can't have dropped off. It has to be at worst at the point of going slack. It has to be at worst the point of reaching 0. Now we can put in what the v squared bit is into all of this. So that is giving us mu squared over L minus 4mgl over L, so minus 4mg, and then minus that other mg, and that's got to be greater or equal to 0. We can get rid of all these m's. So we've got that u squared has to be greater than or equal to 5gl. So that's giving us the minimum value. We have to set off with a value of u which is greater than or equal to the square root of 5gl. Otherwise, we are not going to make it to the top. If we set it off with exactly the square root of 5gl, then it will get to the top with 0 tension in the string. It will be absolutely on the point of going slack, but then it will tighten up again as we go past. So that is our limiting, our minimum velocity in order to have circular motion. So of course that's assuming we've got no friction and all that, but and any other losses, but we're not putting losses into this. But yeah, hopefully you'll be able to see how similar that is to what was going on with a drum. We could have done all of this again with a drum rather than a string. Nothing's changed. We're just changing tension to reaction force. It's still the same thing. There's no changes whatsoever about this. Yeah, we're just saying, well, yeah, now we've got something that's pushing it. We've got a reaction force pushing to the center rather than a tension in a string that's pulling it towards the center. But all of the analysis is exactly the same. So don't think we've got multiple types of circular motion question per setup. It's all the same analysis, which is of course what we want in this. We don't want to be changing our analysis for setup. It's completely reusable.